We have just a little bit to do finishing chapter 17, and then we'll move on to 18. Your study guide for 18 will be posted today. I'm running a little bit behind on that as well. All right, so we've been talking about enolates, and last time we talked about two methods to alkylate and enolate at the alpha carbon without having to worry about these strange complications. And I'll just show you one of these, but recall that if you take a beta keto ester, it's quite easy to do the complete deprotonation of the alpha proton, which is alpha to 2 carbonyls because its pKa is so low. You can generate the enolate in quantitative yield and then introduce the alkyl halide, and that gets you to the alkylated molecule. And then we said if you add acid and water and heat, you do two things. You hydrolyze the ester, you do the decarboxylation reaction, and then you tautomerize. And basically that process causes you to lose this part of the molecule and everything else remains behind. And so what you're left with is, let's see, 1, 2, 3, this new ketone. And you can recognize that this product is something you could have gotten from this synthetic pathway by virtue of the fact that it is a methyl ketone. Now, I think last time we went ahead and put 2 alkyl groups on the alpha carbon. You can do that. You can also not. You can make rings. And the key step in the decarboxylation was this beta keto acid intermediate, in which the beta carbonyl group could engage in an intramolecular hydrogen bond with the proton of the carboxylic acid. And then the following happens: lone pair electrons attack that proton, electrons kick down and kick off the enolate as a leaving group, and your first immediate intermediate is this enol, which goes on to tautomerize to the methyl ketone, and of course you lose CO2, which is irreversible. So that's decarboxylation, and I didn't just introduce it to make your lives more difficult. That was not my only reason, but rather, okay, sorry, that hit way too close to home. I'm sorry that I'm making your life difficult. Occasionally I run into students out and about in the community, and sometimes they have significant others with them, and I always apologize to the significant other for the pain I am inflicting upon the relationship. Flashback sequence. It was the year 2000, and no, maybe it was 2001. Anyway, I was newly back from the mission, and I was taking organic chemistry, and I was also dating Amber, who's now my wife. And at one point, I could tell she was kind of frustrated, and we were driving this old. One of the things about dad stories is there's lots of extraneous and irrelevant details, so just come on. We were driving this old 96 Mercury Sable. It was a grandma car, but we were driving down on University Avenue, and I still remember this conversation, and I thought, are we breaking up? Because she didn't feel like I was prioritizing our relationship, and she said to me, I just like, don't you want to spend more time with me? Don't you want to see me at all? And I said, thinking about all the homework I had to do, and particularly OChem, I said, well, on Wednesdays I might. And that was not the correct answer, let me just say. And I learned over time to prioritize things better and make time for anything. Anyway, I know what you're going through, and I'm sorry for the pain I'm inflicting on you and your various relationships. But I'm going to give you more to learn, so we're just going to keep going. So decarboxylation is important in biology, and so I want to show you, we'll encounter it again when we talk about lipid metabolism, but I wanted to give you an example that your text gives you on how your body takes amino acids and converts them into neurotransmitters. So the amino acid, and it involves decarboxylation. So the amino acid, let's see, histidine looks like this. Do you have to memorize the structure of histidine? No, at least not yet anyway. And it looks like this. And your body can take a cofactor called PLP, which we've seen before, do a decarboxylation reaction, and convert histidine into the following just amino compound. And this, when histidine is decarboxylated, it becomes histamine, and that's important in allergic responses. And when you take these antihistamines, it's about inhibiting the synthesis of histamine. So how does this happen? It actually involves a little bit of imine chemistry. So we're going to use PLP, which is Periodoxal Phosphate. Do you need to memorize this structure? No. We've got an aldehyde here. You've got a phosphate group here. So what happens in this reaction is that we form the imine, and I'm not going to draw that mechanism because you already know it, and you can go back to your notes and take a look. We're going to form an imine between this nitrogen and this aldehyde, right? So once we've done that, the product should look like this. I'm going to just represent the amino acid side chain as R there. Okay, and of course, at physiological pH, that carboxylic acid proton would be gone you'd have the carboxylate. Now, if you look at that molecule, I want you to look at similarities between the molecule shown down there and the beta keto acid that we used for decarboxylation before. Notice that with the beta keto acid, you had a carboxylate on the carbonyl carbon, then an alpha carbon, and then a carbonyl group on the beta carbon. And the idea was that if CO2 left and kicked off this portion as a leaving group, we would have a negative charge in a place where it could be resonance stabilized. Well, similarly here, you have a carbonyl carbon, an alpha carbon, and a nitrogen that's doubly bonded to something. And that thing to which it's doubly bonded is also conjugated to a benzene ring. So think about this. If I were to imagine all of this, all of that as the leaving group, I could imagine electrons on the oxygen kicking down to, and I'm just going to show these lone pairs going on to the alpha carbon. So we would lose CO2, and what would be left would be the R group and a negative charge here. But notice that the PLP portion of our molecule already has a positive formal charge on it, and that ring is conjugated with the imine. So we're not going to be surprised to notice that we can draw a resonant structure where we move these electrons down and get a neutral molecule. Okay? So that's where we lose the CO2. This is a resonance stabilized intermediate. You don't really need arrows to convert one resonance structure to another. There's no motion of electrons going on here. It's just these are both valid descriptions of the molecule that we have here. But the idea is that this portion of the molecule serves as sort of an electron sink to delocalize the negative charge that's left. So getting to histidine at this point is a matter of protonating the alpha carbon to give us, I was going to copy and paste, but I decided not to. Protonate the alpha carbon. So now we don't have the negative charge on that, what used to be the alpha carbon anymore. And then we'll simply hydrolyze the imine, and I'm not going to show you that mechanism because we've done it before. Briefly, that would involve protonating the imine nitrogen to generate the iminium. Water would attack to give us a tetrahedral intermediate. We would do proton transfer to trade who's the good leaving group, and ultimately an amino group would get kicked off. This portion of the molecule becomes histamine. Okay, so that's a decarboxylation reaction, and not surprisingly, it is catalyzed by an enzyme called a decarboxylase. And nature's using the same basic principle that we used above with the beta keto acid. If you have something attached to the alpha carbon that can resonance stabilize a negative charge, then decarboxylation can happen. All right, questions? Okay, L-DOPA is made via this method, only using the amino acid tyrosine, which has a phenol side chain, and then L-DOPA is modified later on to become dopamine. Serotonin as well, I think, comes from the amino acid tryptophan, which is decarboxylated to form serotonin. So it's just beautiful how resourceful the body is, rather than come up with many different sorts of sources for materials. It uses the same materials in multiple different ways. Okay, so the last thing, anything you want to talk about there? Yes, sorry.
What does PLP stand for?
Good. PLP is the name of this molecule, and it stands for Periodoxal Phosphate. This portion is pyridine, so that's where the pyr comes from. I assume ox is for one of the oxygens, maybe this one, and then al is for the aldehyde, and phosphate is for the phosphate group. But when you take biochemistry, you get tired of all these big names, and so you just abbreviate them with acronyms as much as you can. What else? Yeah?
So that circled part becomes the histamine. Where does the 5-membered ring come in?
That's the side chain, sorry. So I started, after this point, I abbreviated the side chain as an R group. Yeah. What else? Okay, cool. So there's one last reaction from chapter 17 that we're going to talk about. It's not hugely important, though it is useful from a synthesis point of view. We're not going to spend a huge amount of time on the mechanism. The reaction is called alpha halogenation of carbonyl compounds. And basically the idea is that you use bromine and then you need acid Usually acid is present. This is acetic acid. This is both an acid for the reaction and solvent. And that will install one bromo group on the alpha carbon. It turns out you can run this reaction under basic conditions as well, but that's something that we're not going to worry about, in part because there's some complications. The basic mechanism is that under the acidic conditions, I'm just going to represent our acid this way. Under acidic conditions, we protonate the carbonyl oxygen to generate the oxonium ion. Then, probably the conjugate base of our acid can remove the alpha proton, and this is the tautomerization process that gives us the enol. All right. Now, in the presence of Br, BR is an electrophile, and this is an enol, but we shouldn't be surprised because we've thought of enolates as nucleophiles. We shouldn't be surprised that enols can be nucleophiles as well, because for this enol we can draw a resonant structure wherein the alpha carbon is negatively charged. And so we can draw this step of the mechanism in a couple of different ways. We can show electrons on the oxygen kicking down, breaking the carbon-carbon pi bond to attack bromine. And then you're attacking the bromine-bromine low-lying antibonding orbital, which breaks that bond. Alternatively, you could just start from this resonance structure and have the alpha carbon attack the Br. Either way, you get the following oxonium ion as the product where you have installed bromine on the alpha carbon, and that's why we call this alpha halogenation. At this stage, then we would have some base remove the proton on the oxonium ion. I think your text shows Br minus doing that. I really don't like that because Br minus is a terrible base. But so we're going to be sort of agnostic about what it is that's actually doing the deprotonation here. In the end, your product, though, is this alpha halogenated carbonyl compound. Yeah?
So if it weren't symmetrical, would it just go to more substituted?
Good question. If it weren't symmetrical, would it just do more substituted? I think that's probably right because these are equilibrium steps, so you'd probably get the more stable enol. I don't recall your text being that focusing on that issue for this reaction. Now the point of doing this is your text puts it in here because it's just another example of a reaction at the alpha carbon. But these alpha halogenated molecules are useful synthetic intermediates because all of a sudden you've got a good leaving group there that you can do SN2 and E2 chemistry with. So let me just give you a couple examples of what your text shows as a possibility. The first would be, let's see, Br2 with acetic acid to give you the alpha bromo ketone. And then if you add a nucleophile, for example, this thiol, you can do the SN2 reaction, the substitution reaction where you install a nucleophile at the alpha carbon to a carbonyl. So from a synthetic point of view, looking at pattern recognition and retrosynthesis, when you have a product with what could have been what used to be a nucleophile now attached to the alpha carbon, you want to be thinking, I could have made that from the alpha bromo carbonyl, which I could have gotten through this halogenation process. Sometimes, and this has to do with retrosynthetic strategy, you look at a product, you say, okay, I think I've seen a negatively charged thiol reacting as a nucleophile before. What would have had to be here at the alpha carbon in order for that nucleophile to have attacked? And the answer is you need a good leaving group, right? So thinking backwards, okay, what would a good leaving group be? Well, if it was a halogen, that would be nice because then I know a reaction that installs a halogen on the alpha carbon. Okay, questions about that thinking and that strategy? It's worth some practice because you're going to forget it, but it's useful. The next idea is we can do an elimination reaction. So I like this reaction because it gets us to a useful starting material that we can use in a ton of other things we've done, but I don't like it because your text is oddly specific on this point. So if you wanted to do an E2 reaction, which base would you choose? Probably tert-butoxide, right? And I say great, that's fine. And that would do the elimination reaction to give you the E2 product, which, interestingly, is an alpha-beta unsaturated carbonyl compound. Now, when you see that pattern, there should be some little lights flashing in your head reminding you of things you can do with alpha-beta unsaturated carbonyl compounds. And we'll mention those in a minute. I will point out, though, that though I'm perfectly fine with you using tert-butoxide here, your text uses a specific set of conditions. And I'm going to write them down here. The text uses a specific base. It's called lithium, and there's two lithium counter ions, lithium carbonate. And then it uses as an additive lithium bromide. The way you write lithium carbonate is Li2CO3. And you'll see the text use this as a base anytime they want to do an E2 reaction with an alpha bromo ketone. Why are they doing that? And who even cares? And to understand this, you have to realize that Professor Smith, the author of your text, is a classically trained synthetic organic chemist. She was trained in the lab of Nobel laureate E.J. Corey at Harvard, and Corey won the Nobel Prize for synthesis of large and complicated molecules. And a synthetic organic chemist, in addition to focusing on reaction mechanisms, also has a huge toolbox of specific procedures to do various organic reactions. And when you go to do a reaction on a real molecule, basically you go to the literature and you find somebody that has done a similar reaction before, and if they have, you try to imitate their conditions because there's no need to reinvent the wheel. And so likely Professor Smith is actually including these two as a specific example of a base that she has actually used before to do this reaction. We're going to pretend like any base will work, but understand the fact that they've included this here is just a practical detail that probably comes from the organic literature. We're not going to worry about the details as to why this might work better than that. Any base, we're going to say that that will not do a substitution reaction is useful. All right. Anything we need to say more about that? Do the E2 reaction to get the alpha-beta unsaturated carbonyl compound, and then recall what we can do with these. Right? We've had cuprates install R groups at the beta carbon. What else have we done? We've had Grignard reagents or organolithium reagents install an R group at the carbonyl carbon. We can use reducing agents like lithium aluminum hydride or sodium borohydride to reduce the ketone to the alcohol. And then I suppose if we wanted to keep the ketone but lose the double bond, we could use catalytic hydrogenation to leave the ketone intact and get rid of the double bond. So there's a lot of different things we could do. Frankly, I'm not sure why I drew this, because this is a boneheaded way to end up with the same starting material that you began with. So we'll just get rid of that, because that's, unless you like going around in circles, which is fun. Okay, so be aware of that in terms of using that reaction in a synthesis, because that's a great way to build up, in particular, carbon-carbon bonds. All right. What else? Anything else? Okay. Well, you thought that things were more complicated now because as we've talked about carbonyl chemistry, the number of things we've been thinking about has dramatically increased. For example, if you take this ketone in the presence of hydroxide in water, we have already talked about how the OH can attack the carbonyl to give you the ketone hydrate. We know that's going on. In general, though, this is a dead end as far as reactions are concerned. So even though that's been going on, we haven't worried about it. And in fact, we have used the very, very small amount of enolate present in solution as a nucleophile, and also recognized that we can make the enol tautomer. Okay? With me so far, all of that look vaguely familiar, things that are going on. If we make the hydrate, we get the hydrate from attack at the carbonyl carbon. We get the enolate and ultimately the enol from attack of OH at the alpha proton, right? Okay. So, and then we've seen, okay, if we introduce an alkyl halide, we can take this enolate and alkylate it at the alpha carbon. Now, the big new concept is to recall that enolates are nucleophiles and that carbonyl compounds are electrophiles. And so there is another thing that can happen and that is for the enolate. I can feel the dread just like increasing. Good, I can feel your anger. The enolate can attack the carbonyl compound at the carbonyl carbon, because remember, at any given point under these conditions, there is like less than 0.1% enolate and greater than 99% carbonyl compounds. So these two see each other in solution. And what can happen at this point is that the nucleophile, and remember enolates react mostly at the alpha carbon, that's the most nucleophilic spot, can attack the carbonyl carbon at the pi star, which is where the LUMO is for that carbonyl carbon, and that breaks the pi bond to give you a tetrahedral intermediate. Okay, so we're bringing together two things you've seen before in a new combination. The business of a nucleophile, forget what's over here. If it's generally a nucleophile attacking a carbonyl compound to give you a tetrahedral intermediate, no big deal, right? You've done that before. And if it's instead the enolate attacking some electrophile to give you some alpha alkylated group, we've done that before, no big deal. The problem is we're just bringing these two things together now. And I want you to not see this as a totally new reaction, but just another example of enolate as a nucleophile and carbonyl compound as an electrophile. So you should be able to predict it at this point what the product is going to look like. Over here, for the carbonyl carbon, we should have a tetrahedral intermediate. So here's our two methyl groups. Here's our negatively charged oxygen. Here's the new bond we made with the nucleophile. Now, what was that nucleophile? It was the alpha carbon of our enolate. And this is the new bond that we made. Okay? And then the question we ask is there a decent leaving group attached to that tetrahedral intermediate? Can these electrons on this oxygen kick back down and kick off anything? Well, they're certainly not going to kick off the CH3 groups. It turns out kicking off the enolate is possible. And what that means is this step where the enolate adds to the carbonyl is reversible. That's an equilibrium step. Now, remember that because later on when we get to metabolism and glycolysis, you're going to see that fructose breaks apart into 2 3-carbon pieces via a reaction very much like this in the reverse direction, where we kick off an enolate and go backwards. So this addition of the enolate to the carbonyl compound is an equilibrium step. If we kick off the enolate, we just go backwards. In contrast, if we protonate the negatively charged oxygen, that will get us to the product of this reaction, which looks like this. So here is the new reaction. And this product, if we want to classify it, is both a ketone and an alcohol. We often call this, because the OH is on the beta carbon, we will call it a beta hydroxy carbonyl compound. So structural pattern recognition has started to be a theme. So because when you see a beta hydroxy carbonyl compound, you need to be thinking, I could have made that via this new reaction of an enolate attacking a carbonyl. Right. Now, the reaction has a name. The name derives from the fact that I think it was discovered with an aldehyde, not a ketone. So it was called the Aldol reaction because if we had a proton here and a proton there, here a proton there, sorry, the product would have been an aldehyde alcohol or aldol. So I'm going to just keep the product that we've shown. And we don't like to make distinctions between aldehydes and ketones when it comes to names, really. So we're not going to call it a ketol reaction. It's just the aldol reaction, independent of whether it's a ketone or an aldehyde. All right, nucleophile attacks electrophile. Questions about that reaction? Yeah. Uh-huh. Why is there less what? Okay, yeah, so counting carbons, your electrophile has 3 carbons, your starting material has 3. So 1, 2, 3, those are from the electrophile, and then this 1, 2, and 3 is from the enolate. Yeah. And that's actually useful for pattern recognition purposes. The 3 carbons from the enolate end up here, right? and then the 3 carbons, the group, the electrophile portion of the molecule ends up here. And this is the new bond that we make. So it can be useful to start to draw beta-hydroxycarbonyl compounds and think about what the starting materials would have been. Other questions? Yeah.
Can this then undergo like decarboxylation?
Yeah, could it undergo decarboxylation? I think you're right that there is the possibility for an intramolecular hydrogen bond. The problem is going to be there's no oxygen here. And moreover, if there were and electrons kicked down, there would not be resonance stabilization on the alpha carbon because this isn't a ketone. All right. Now, one thing you should be aware of is sometimes it's observed that the aldol product goes on to do a dehydration reaction. And the product is an alpha-beta unsaturated carbonyl compound. Your text doesn't really give a rhyme or reason for when you'll see one versus the other, in part because this is an equilibrium reaction, so you just observe the most stable product, and that can vary. It's thought that if there were other groups here that had double bonds that could be conjugated to the carbonyl via this pi bond between alpha and beta carbons, that you might favor this alpha-beta unsaturated carbonyl compound as the product of the aldol reaction. I'm going to accept either option as a legitimate aldol product. So you're never going to have a situation where I say, which of these is the product of this reaction? And I give you both the beta-hydroxy carbonyl compound and the alpha-beta unsaturated one, because it's just both of them, right? I would accept one or the other or both. How do we get to the elimination or the dehydrated elimination product? The mechanism here is kind of interesting. It is an elimination reaction, but it's not E2 and it's not E1. What happens is that it's fairly fast to remove the proton on the alpha carbon, in part because it's alpha to the carbonyl compound. So the first step is you make this enolate, and then once you have the negative charge on the alpha carbon, then electrons can kick down and kick off OH minus as a leaving group. Remember, OH minus is a cruddy leaving group unless you're dealing with an adjacent negatively charged carbon, which surely ought to be strong enough to kick off OH minus. So this mechanism, it turns out this part, the kicking off of the OH minus, is the slow step, the rate determining step, whereas the removing the proton from the enolate is relatively fast. What this means is that though this reaction involves OH, it's a unimolecular reaction because the slow step only involves the one molecule. We will call this an E1 reaction, but it's not a typical E1 reaction where the leaving group leaves and you get a carbocation. Instead, it's an E1 reaction of the conjugate base of your starting material. So they'll call this mechanism E1CB. That's just me sort of nerding out on mechanism. You don't need to remember that term. But you should know the mechanism of removing the OH group via this dehydration reaction where the enolate is the intermediate. Yes? OH is not generally a good leaving group, but when we've dealt with molecules like this before. Do you remember when we had a negatively charged oxygen as an intermediate and we were asking, is this a good leaving group? We sort of compared the negatively charged oxygen to the leaving group once it had left and sort of checked their stability. If the leaving group was about the same as a negatively charged oxygen, we said good to go, and in that case, OH could be a decent leaving group. Similarly here, this isn't a negatively charged oxygen, but it's a negatively charged carbon, and that's fairly reactive because the pKa of this proton should be around 20. So a negative charge that reactive should be able to kick off a leaving group whose conjugate acid has a pKa of 16. The stability sort of matches up. Okay. So you see a beta hydroxycarbonyl compound or an alpha beta unsaturated carbonyl compound, and you should think, could have made that via the Aldol reaction. So let's practice thinking backwards, but before we do that, any questions you want to ask about the mechanism? Yeah?
So if we were working in acidic conditions, would it then be a more, recognizable D1?
Oh, if we were working in acidic conditions, would we first protonate the OH group and it would leave? Probably. Yeah, and I think you actually can do the Aldol reaction under acidic conditions, but your text introduces you to basic conditions, so we'll stick with that. Good, others? So there's going to be a lot of reactions in chapter 18, and some of them are going to have different names, but they're all going to involve the same basic mechanism. Enolate attacks carbonyl compound, and then just as before, what happens next will depend on whether we've got a good leaving group on that carbonyl compound. So I want to practice recognizing products of aldol reactions. So I'm going to draw a product sorry, that's not what I wanted. Okay, I want you to look at that and then think, if I did this via the aldol reaction, and this is our retrosynthetic arrow, which means what did this product come from? And if I want to do it via the aldol reaction, what were the starting materials? So go back to your notes and look at the alpha beta unsaturated carbonyl compound and think about how to break that up in your mind conceptually to the starting materials of the aldol reaction. If you want, you can think back one intermediate step. Remember that the alpha beta unsaturated carbonyl compound came from the beta hydroxy compound. Oh man, I'm erasing things instead of using a pointer. So what would the corresponding beta hydroxy carbonyl compound be? Does that look familiar? Does that look reasonable? Okay. You're almost there. Now, what would the starting materials have been? Remember where this OH comes from. Remember how we talked about our beta hydroxycarbonyl compound. This portion comes from the carbonyl group that was attacked, and this portion comes from the enolate, right? And this is the bond that we made. So you can think back just one additional step. The nucleophile would have been this enolate, And the electrophile would have been this aldehyde. And actually, we could have got that enolate from that aldehyde. So if you were to propose a synthesis for this reaction, it would simply be the aldol reaction of this aldehyde with itself to give you this product. Okay? Now, this is going to be fun and painful. I'm going to give you this one. Oh, it's a ring. All the little SpongeBobs are running around in your head now, and the place is on fire. You can make this alpha beta unsaturated carbonyl compound from an aldol reaction. Okay? So I want you to figure out what the starting material would have been. Along the way, you're going to have a question, and that is because your starting material is going to have non-equivalent alpha protons, and you're going to wonder, where do I deprotonate and why? And you might discover that to get this product, you have to make a less substituted enolate. But remember that the aldol reaction is an equilibrium, so what product you get is ultimately defined by what is the more stable product. Okay? Before, with enolate alkylation, making the enolate was in equilibrium, but once we added the alkyl halide, that broke up the equilibrium and we were done. With the aldol, once we make product, we can go back to starting materials as many times as we want. So, work on this, figure out what the starting material was, and draw the mechanism. And I'll see you next time.